I'm going to show you demonstration about the Faraday's experiment and that derived Faraday's law. So Faraday discovered Faraday's law in 19th century, and we also have 19th century old demonstration kit similar to one Faraday's was. Alright, so what I have here, I have primary coil. This is primary coil, and this one is secondary coil. Is same, they are same like a solenoid. So primary coil is connected to the battery, and secondary coil is connected to the meter, similar to here. So I have primary coil here, which is connected to the battery, and secondary coil is connected to the meter. It's called galvanometer, but this is same as ammeter. And there is, make sure you understand, there is no connection between electrical connection between primary coil and the secondary coil. And we are going to see how the current is induced in the secondary coil. So first I'm going to do here, turn the battery on, right? I have switch here, so there is no current right now. So if I turn close the switch, we will flow the current and see what will happen in the galvanometer. Okay, there is little bit displacement of the needle, and if you want to see the more deflection, I'm going to put the rod, which is iron rod. So iron is ferromagnet, so we will have more magnetic field. Alright, so with that magnetic field, I'm going to turn on the switch again. Okay, there is big deflection to the right, and I'm still closing the switch. That means there is current flowing right now. So if I open the switch, see what happens again. Now the deflection is to the left. So what do you think? What is the reason for current in the secondary coil? Is the current in the primary coil induce the current in the secondary coil? Right? Okay, now I'm going to do one more thing. I'm going to remove the primary coil. I'm not going to put the current anywhere. So turn this off, and I'm not going to use primary coil. I just have the secondary coil, which is connected to the galvanometer. And I have now here magnet. See, it attracts. So this is magnet. So I'm going to move the magnet. I don't know which side is north pole or which side is south pole, but I know one side is north pole and another side is south pole. So I'm going to move this into the secondary coil and see what will happen. See, it is deflected to the right. Now the magnet is inside. That means there is a magnetic field, but there is no current. And if I remove this again, see what will happen. It went to other side. So what caused the current in the primary, in its secondary coil? And remember, there is current only when I insert it. At the moment it is inserted, it goes back to 0. And when I remove this, again there is a current, and then it goes back to 0. So what do you think? What actually caused the current in the secondary coil? What induced the current? So Faraday's, after the experiment with the Faraday's, so Faraday discovered the induced current is because of the changing magnetic field. Okay? Change is the key word here. So let's go back again. If there is a change in the magnetic field in the secondary coil, when there is current or not. And if there is a change in the magnetic field in the secondary coil, when I move the magnet. And remember, the direction of the currents are opposite when I insert the magnetic field, a magnet, and remove the magnet. And also, let's show you, if I insert this one, current is to the right, I mean current is flowing this way, we can say. And if I remove this, current is flowing to the other way. So if I reverse the magnet, see what will happen. The current flows in the, also in the reverse way. If I remove, that's also reverse way. So direction of the current depends on how the magnetic field direction is changing, and that is part of the Lenz's law. Okay, so here the Faraday gave the relation. The induced EMF is equal to change in rate of change of flux. This is magnetic flux. So it depends on how fast the induced EMF. This is same as something like there is a battery connected. There is a battery connected, and then the voltage induced by this induction is induced EMF. It is not battery voltage, but this is same as battery voltage. When I move the magnet, it is giving the current as if we have a battery inside. And the voltage induced is E, which is equal to delta P by delta T. And if we have many turns of coil, then this will be delta P by delta T. Okay, this is about how fast. So now I'll show you what does that mean. So if I insert this, if I insert it slowly, the current is small, right? Current is small. So if I move it very quickly, you will see big current. And again, if I remove it quickly, you will see big current. So that's what it means. It is not how much magnetic field or how much. This is actually flux. Flux is same as electric flux, but here it is magnetic flux. So it is the rate of change of magnetic flux is equal to induced EMF. It is voltage. So when I have a current in the primary coil. And turn the battery on. And if I set the current, there is an induced EMF. There is current in the secondary coil. So does it make sense with the Faraday's law? So we learn when there is a current in the coil, it produces the magnetic field, and that magnetic field is coupled with the secondary coil. So this is actually coupled with secondary coil, and this one you can think about like a core, this iron rod. So as soon as I close the switch, there is a change in current from 0 to certain value. So in the same way, magnetic field also changing from 0 to a certain value. There is a change from 0 to a certain value. So during that time there is a change, and during that time there is change in magnetic field in the secondary coil as well. So that's why we got the induced current. So let's see again. So if I close the switch, during that time there is the induced current, and while there is a current flowing, there is magnetic field, but there is no current. because the magnetic field is not changing. Now if I open the switch, there is a change in the current from certain value to 0, but this is opposite direction, it is decreasing. So if I open that, then we can expect there is a current again, but it's in a different direction. Okay, so we will discuss more about the Faraday's law in the lecture.